Welcome to the Neurolace Talks with guest Andre Watson, host Micah Blumberg, edited by Adam Alonzi.
I see myself mostly spending time between the world of engineering biological systems and material science and engineering as relates to making nanoparticles to deliver genes to different places in the body. So what I spend my day-to-day really building is my company, Ligandal, where we are using ligands, or things that stick to different markers and things like receptors, to guide these vectors for gene therapy to really specific locations in the body. And
That's fascinating.
Have spent a lot of time on thinking about synapse physiology. I was going to go to McGill for a neuroengineering PhD, but I decided to come out here and work on this. So I really love pharmacology, and for me, understanding consciousness, or at least a piece of it, is incomplete unless we try to look at the molecular picture too.
Yeah. Yeah, I agree.
So it'll be really fascinating to talk about maybe how that plays a role in the future of the human experience, and also how we're going to build machines that capture various aspects of human intelligence. In there.
Yeah. Okay.
What got you on this journey?
Yeah, so what got me on this journey was a book called On Intelligence by Jeff Hawkins, and so he was a neuroscientist, started the Reading Institute, and he was also the president and founder of Palm, made the Palm Pilot and the Palm 5 and the handspring device, and then eventually that sort of then iPhone came along and sort of took over the market. So the Palm went away. So what Jeff Hawkins did instead was he started a neuroscience research institute, and he wrote a book called On Intelligence, and he started this computer company called Numenta, and Numenta has their whole idea is to basically create a computer that's based on the neocortex. And so this computer uses what they call hierarchical temporal memory. And they say the neocortex is like a hierarchy, and the top of the hierarchy is the thalamus. And so hierarchical temporal memory means that, and basically you're sort of describing the structure of a neural network, like as if a deep learning network is specifically structured like a hierarchy. And so the lower levels of the hierarchy would just focus on the lines and edges and bits. And at a higher level, you turn the lines and edges into the computer recognizes a concept, because it's like a statistically relevant coincidence pattern. And then at a higher level of the network, you have the computer begins to put together the concept of eyes or words, or it's basically a map of the associations of the lines and edges but at a higher level, the computer says this is an eye, because that's what the neural network represents with its weights at different levels. So basically, he was describing in his book On Intelligence, he was describing deep learning, which was sort of like this. So the neural networks have existed since the 80s. A lot of the great designs for computers came from the 80s, but now that since 2012 we had some new ideas about how to make the neural networking deeper. So they called it the deep learning, because you could only get about 3 layers deep, and now you can in some cases there are neural networks that are 300 layers deep.
My curiosity as these technologies evolve is the level at which we'll really be able to understand and or emulate the human experience. And that's something that would be really interesting to discuss with you, because I've spent a lot of time thinking about synapses and sort of how things build from a really bottom-up level, just, molecular pharmacology, how different drugs and ligands and things in your brain bind to these different receptors in order to create all these different effects. And something that I've learned through studying that is the amount of layers within even a single synapse of the gradients of state that can exist at any given point in time to represent any range of things that are not just a 1 or a 0 or an on or off. I feel like that is something that isn't talked about very often or frequently. And I'd like to at least think about and sort of forecast, as we build these technologies, an EEG can tell you some basic things. And if you have a direct interface or some more advanced technology, you can learn a lot more. And certainly, even with existing fMRIs, we're able to recreate visual imagery that our brains are seeing based on the fMRI data on its own. And so, as a starting point, there's definitely a possibility for having some interfaces. The question is, a lot of people also speak about these technologies eventually being able to completely function as humans or transcend humans. And while I believe that we will have different AIs that will do different things, I really wonder if we're going to see humanity become obsolete or kind of the core driver of all of the peripheral artificial components that become the future of humanity.
Sure, and I have thought about that because so do you remember Steven Spielberg made this movie called AI Artificial Intelligence, and in the movie, it was good. It was good. It was a vision of what the future might be true in the future. Definitely worth checking out if you haven't seen it. But one thing that in retrospect, the movie was fine when I saw it. In retrospect, I do have one small gripe with it, and that is that the humans made the distinction between mechas and orgas to say that you're a mechanical robot, you're a mechanical person, and I'm a real person. And so this is like see, what's interesting is, you say, well, what's an orga? An orga means organic, means grown. And mecha means made in a factory or something, artificial. But okay, so the thing is, and I've heard people describe this concept in other ways. We're like, if we're robots, we're, organic robots, or we're kind of like closer to being trees, and this is like, we're not metal robots. We could have a soul, and so it's not possible for machines to have a soul because they don't have the same sort. These are things I've heard people say, and I think that we are metal robots. And so there won't. And I said because
meta or metal.
Metal. I think humans are metal robots, because our nerve cells, for example, are filled with metal, filled with in the outer sac filled with calcium ions, and on the inner sac filled with potassium ions. The calcium ions are, the positively charged, and the potassium ion. Is the potassium positively charged?
It's also positively charged. I guess, if you're saying metal in the sense that it's capable of conducting ions in the presence of a variable solution of electrolyte concentrations, then, we could redefine metal for the purposes of this, though from, strictly speaking,
calcium
that's not a metal
potassium
solution.
You don't consider calcium and potassium to be metal.
Not if they're in solution.
Okay.
Well, wait. Hold on. Let's pull
on the table of elements.
We've actually got a periodic table on.
Yeah.
Hand, so let's pull this up. I mean, they're definitely, in the strict sense, they are alkali metals.
Yeah.
Going down from lithium to sodium to potassium.
Yes.
Well, and then
thus I said we are
the alkaline earth metals. I suppose that is a really interesting way of putting things, because by moving around all these positive charges through active energy expending processes, we're able to control not only the action potentials, but sort of the arc of the shape of our firing and
of a magnetic field.
Yeah, at a really just fine, superb level of electrophysiological weirdness.
That's why I like to say I believe that consciousness is magnetic, because our brains are manipulating a magnetic field.
It's so interesting.
And that we are metal robots. And once we solve creating robots in a factory, they'll be no different from humans. They'll just be, and people will not say, oh, this is surprising. People will say, oh, of course it makes sense. The universe is a fractal. And they'll be like, okay, well, no big deal then.
The interesting thing to consider is the basis of the kind of consciousness that we have versus the kind of consciousness that a machine intelligence would have. Because we've entirely evolved, even from the time of being single cellular organisms, to feel the world around us in the form of receptors binding to different molecules. And you can think about the electrical part of our biology and our consciousness, but there's also, at even the most baseline resolution, a physical sensing one. And we are built out of these exquisite nanosensors that have the ability to distinguish serotonin from dopamine and a range of thousands of different compounds from each other. And this is actually, I would argue, one of the core facets of our consciousness that cannot be adequately modeled through electrophysiology alone.
Okay, explain that one again. You said, why can't we model that by it?
Well, we're starting from a position of biology by its baseline interacting with its environment. To use an example of the sort of sensing that a biological cell can have, you have this family of cell surface markers known as integrins. Mm-hmm. Integrins bind to collagen, elastin, these different extracellular matrix proteins that form the mesh of what comprises your skin and all of your tissues. And through binding to these surface markers, these receptors, the receptors are actually mechanosensory. As you pull on the strings, so to speak, mm-hmm. they engage signaling cascades that are so precise that they can upregulate themselves and produce more of that specific protein or more collagen and things like that, as well as things to remodel the matrix or break it apart and chop it up with these things known as matrix metalloproteases. And this is just one example.
Describe that matrix.
So you have an extracellular matrix of, we think of cells as having, we have, 70 trillion cells in our body. And those cells are not just floating around freely. Right. They're interacting through a series of proteins, glycoproteins, like sugar proteins, sugars, lipids, glycolipids, and you name it, that are all latched together. And amidst all of that randomness that you perceive, if you were to just map what all these things are, we're able to derive very specific information where pulling on a single receptor that is bound to by an extracellular matrix protein can trigger very specific signaling cascades that cause remodeling of the entire system around it.
That's interesting.
And this is no different with neurons. If you think about a neuron and the axon and the dendrite being latched together, people always think of them as they're just sending signals and it's just electricity. Have you ever wondered why a dendrite sticks to an axon?
Yes.
And that's the same thing, actually. It's an extracellular matrix that holds them together. And you have these different surface markers that latch the axon to the dendrite physically. So you have, for example, this family of proteins known as netrins that bind to netrin receptors. And they're one of the major extracellular matrix components that hold together axons and dendrites.
What are their electrical properties? I mean, you don't want to have because you need the synaptic gap for the chemical mm-hmm. synapse. So whatever's connecting the two you can't have electricity running across that because otherwise it would defeat the synaptic gap. So the properties must be inhibiting electrical signals somehow.
I think there's still a space there. I think it depends on which protein you're talking about. And I think for the purpose of thinking about how the potentials are propagated, it is really hard to envision the scale at which this is interacting because there are 20,000 proteins and thousands of these proteins exist on the cellular surface, and mm-hmm. they don't need to be homogeneously tight junctioned in order for them to be serving their functions. You can have a distribution of a lot of things that aren't going to negatively impact the way that a cell functions.
Okay.
So, I mean, anything that we would say about that would be completely speculative.
Yeah.
But I guess where I'm going with this is that...
Well, someone was saying that, the deep blue, not deep blue, but the guy who's working on the blue brain.
Yeah.
He was saying that they created a model, a computer program to try to simulate where synapses where where they would connect, where cells would connect. And they said that basically what they found out was the computer model was able to, they basically did it randomly, and it was like pretty much close to what actually happens in the real brain. So they're saying that basically in the beginning, when people are born and their synapses are first growing and connecting, that it's basically like random. And so
well, what does that mean?
But I mean,
what does it mean for it to be like the brain? Because it's one thing to have a small set of neurons.
They were specifically stimulating just how neurons would form their initial connections with each other. So it was basically it's a controlled experiment. And so in reality, there's so many other factors that could be tilting that. So yeah, you can't, when you have a model on a computer, it can't compare it to the bizarre reality of a real brain.
Well, one of the things there that I really wanted to talk about is the nature of kind of, we can call it the now brain versus the evolving brain.
Yeah.
Or if we want to say it perhaps in terms of pharmacology, the ionotropic brain versus the metabotropic brain. So when you think of an action potential, when you think about these metal ions flowing in and out of the cell and being pushed around to change the way that charges work, that's ionotropic.
Oh, you're talking about the glial cells, metabotropic. No.
I'm talking about every neuron, every receptor that generates a quote-unquote signal.
Mm-hmm.
You can have ion or voltage-gated, you can have basically voltage-gated channels for ions.
Yeah.
That can either respond to a neurotransmitter or to some voltage changing on the cell surface.
Sure.
That's all quote-unquote ionotropic by definition.
Okay.
Metabotropic is everything else. And so most serotonin receptors, every dopamine receptor, as you go through the thousands of receptors, like 800 receptors that are G protein coupled receptors, they're actually the most common protein in your body.
Mm-hmm.
You have about 800 of them. So all dopamine receptors, all but one serotonin receptor are G protein coupled receptors. They have all these different subclasses.
That in of itself is a ton of calculation, chemical calculation.
Exactly. And
so it's like a chemical computer versus an electromagnetic computer.
Yeah. So think about this,
but
right?
The thing is, all the chemicals are doing both at the same time.
Not all of them are.
No?
No, a lot of them aren't doing electrical things directly. Some of them are changing the way that receptors.
Well, what I'm saying, as an aggregate, as a whole, they'd be affecting
the ionotropic brain.
Yeah.
Yes. And the interesting part is that if I could capture a perfect snapshot of your brain over 30 seconds of every neuron, every astrocyte firing, I would learn a lot about you. And I could see that you're having these changes occur in your brain. And
sure. But that exact pattern would probably never happen twice.
Exactly. So how do you model someone having more or less testosterone, or being on LSD or not,
if they never have the
in your
same
neural network, if you only capture the ionotropic parts? How do you predict how each brain will change?
Well, I mean, okay, so I mean, I think, okay, so like, I guess in terms of, consider diffusion tensor imaging, right? You'll
have to tell me more about that.
So they blast a radio signal at the water in your brain, and it's a specific frequency, and it causes the water molecules to release energy, which is at a specific frequency. And so you have a camera waiting on the other side. So the magnet, the big giant magnet, what it does is that's it's getting your molecules aligned, and then they hit it with a radio frequency, and when the magnet stops, and then am I doing that wrong? But anyway, so maybe I'm describing it incorrectly, but
well, what is
the magnet gets your waves aligned, and so they blast. I'm pretty sure they blasted with the radio signal, but they have to stop the magnet first. They blast it with the radio signal, which and then the result is you emit like lambda waves or something from all the water particles that were aligned. And so the water now has to travel. It can't travel. It's once it's released by the magnet, it has to travel along the axonal fibers. I mean, it can't travel freely like it would if it was just in the ocean, right? And so because it's emitting that specific frequency while it's traveling along a specific line, and you're capturing it from a specific angle, like you have a camera that is doing an X capture, and a camera that's doing a Y capture, and a camera that's doing a Z capture, at least 3. And then you can do tensor calculus on it and figure out the position and direction of those water molecules, so they become your tensors.
What resolution of data do you get from that?
So with the standard MRI or DTI image, I believe is the voxel size. You could fit in like 1,000 or more, or a lot more, in neurons in a single voxel. So it's really not that detailed. But idea here is you create these. I don't know if you've probably seen diffusion tensor images where they have these. They're really colorful images of the brain. Yeah, so they're really colorful, like brain scans. I'm just go.
And it's MRI based. I see. I didn't follow that it's using an MRI.
Yeah, so the MRI is just like a 2-dimensional.
So this is how you kind of keep track of the tracks.
Yeah.
Right. Yeah, I've seen a lot of these.
So my hypothesis is if you did like 3,000 photos. So you see, they only need really 3 photos because you're just getting the basic geometry. I think if you did 3,000 photos, sort of like using like a light field type of camera, like the new Litro rig where they have like 91 cameras all pointing in the same direction. If you did that kind of DTI, and then so you kind of like trying to figure out the light field of the brain, not only where the water molecules are and which direction they're traveling, but also you're figuring out the direction of the frequencies that are traveling towards the camera. That's the light field. And so you could create like a hologram that has potentially a higher resolution if you're using a lot more images. And you're gonna have to use a technology like videogrammetry, which is like photogrammetry on every single frame. So that's the proposal for a new kind of DTI. DTI is not limited to MRI. A lot of people confuse it. Actually, the diffusion concept is MRI, but what I mean is that what it really is, it's tensor calculus, it's tractography, and you could apply that concept to other types of brain, other types of sensors, whether they're inside, whether they're implanted inside. So if we put sensors inside, like these doctors, and you could, if you have at least 3 of them, then you could calculate. You could calculate the whatever you could calculate. You could do some something like tensor calculus on to map all the ions within a specific field that you decide to focus on with your sensors. But you could also do something like this with EEG or MEG. Do this with sensors that are just sort of like pointed at your thalamus from your nose. Just point them straight up the nasal canal, or shoot a sensor up the nasal canal as far as you can get it without breaking something. It's very tasty.
We were drinking yerba mate.
Yerba mate, yeah.
Sponsored by Guayaki.
There was one thought that I had about, so you and I on the phone were talking about the synapse, and you were talking about how astrocytes and oligodendrites have all these interesting, this is part of what you study. They have all these interesting properties in terms of their networking and the back propagation and how all, it's, so basically there's this whole, like people think of, people think of, people in computational neuroscience think that the brain's all about the neurons. There's you mentioned that there's an ionotropic brain and a metabotropic brain. There's, in a sense, you could also say there's a neural net and then there's a glial net, and that these two nets are interfacing. And
there's so much complexity there, both in terms of how the neurons and the astrocytes and the microglia interplay with each other.
And does mitochondria talk to other mitochondria? I mean, maybe there's a mitochondrial net too. I don't know.
that would be interesting. I mean, I'm sure they're connected via. There are mitochondrial localization signals, like protein sequences that directly go to mitochondria, but I mean, I'm sure microtubules connect mitochondria as well. But I don't know what the intra-mitochondrial signaling looks like, other than this sort of network of the electron transport chain. But we're digressing.
Well, sure. Well, okay. So So I mean, really. So this podcast is about neural-lace, and there's so many different potential ways to interface with the networks of the brain. It doesn't have to be an ionotropic interface. You could potentially also do a chemical interface. A metabotropic interface.
It's going to be harder.
Sure. And I think that, but there's something special about how the metabotropic interface is influencing the ionotropic interface, I think. I mean,
I think that is everything in terms of how we dynamically change throughout time. If you imagine kind of the picture of the neural tract that you mentioned through the data of the fMRI.
Yeah. Oh, DTI.
DTI, right.
Yeah. Diffusion tensor imaging.
Yeah.
Or tensor calc.
Right.
Tensor calculus applied to brain imaging.
If you look at those tracks, how do you and what do you need to determine in order to have a snapshot of the person's consciousness in a way that captures the subjective experience too?
Okay, so this goes back into, so let's say we're never actually going to capture the same brain signal twice, for the same reason that you're never going to capture the same photograph twice. And that the universe has one direction as far as we know because of entropy, because of, that's entropy is time, right? And so you're never, it's like, but here's the thing is we're able to identify objects in this bizarre world. Like I know, like I'm holding right now headphones in my hand, and I recognize they're headphones, but I've never seen headphones from exactly this angle, exactly this way, with exactly this room, with exactly this lighting, with exactly this, time. It's all brand new, but it doesn't mean we can't identify stuff in it. So it's just like, that's why using neural networks to decode brain activity is going to work, because we can identify the pattern of broccoli in our real world. And if we were able to look at brainwaves long enough, if we had the senses to understand brainwaves long enough, then we could identify broccoli in our brainwaves.
What do you mean by broccoli?
Broccoli, what I mean is that the idea is that broccoli, we learn to know the taste of broccoli because, well, let's look at how does it, a good analogy is to look at how does a self-driving car recognize if it can move forward or not. And so you dive into this topic, and it's how neural networks work is useful to talk about, because then you can start to have ideas about how our brains are working. So if you say, well, a neural network is recognizing that there's a car in front of its path, it's recognizing that something is in front of its path. Well, how is it recognizing that? And well, you say, well, there's cameras that are pointed at this car that's in front of the car that's driving. Maybe let's just say use a tree. There's cameras pointing at the tree that's in the path, okay? And the cameras are breaking video down, and there's also LiDAR and a bunch of different sensors. The cameras are breaking down the video into pixels and frames and then pixels. And the neural network is putting together all the little different, at the lowest level, it's putting together it's putting together, whether there's a line or an edge or a color. And at a higher level, it's, recognizing, well, this is a long line, or this is a curve, or this is and then at a higher level, this is a leaf.
Yeah.
And another part of the network is saying this is another leaf, and another part saying this is another leaf, and another part says this is a branch.
Yeah.
And at a higher level, it says either this could be a flower or this could be a tree.
Yeah.
At a higher level, this is definitely a tree.
Yeah.
Right? And so the idea is that our minds are basically doing the same thing.
Yeah.
Where your eye has tons of receptors in it, right? It's tons of sensors, light sensors, blue light sensors, and you have these photons that are bouncing off your retina, and they're causing proteins to flip. And as the proteins flip, the ionic charges displace eventually, and then eventually there's this, you have this separation of positive and negative charges, and there's an action potential, and all these neurotransmitters get released throughout the network of the brain. And people see, well, they see, oh, I think there's a signal traveling from the eye along the optic nerve to the thalamus and then back to the occipital lobes and parietal lobes and the rest of the brain activity. And we're like, well, we see this signal, and we're like, and the question is like, well, what is a brainwave? Because we see these signals and they're being triggered, and what is a brainwave? And a brainwave is like, seems to be triggered by these incoming signals. Somehow you have the incoming, something that you see. The idea that's popularized is that photons are bouncing off of that, and they're bouncing off your eye, and then they're triggering brainwaves. And these brainwaves, they have characteristics that in time, like frequency patterns, and they have characteristics in space, right? And your brain as a network is processing brainwaves that have their spatial and temporal patterns. And this is the kind of information we see moving all around on the ionotropic level. And so the basic idea is, I'm thinking that, if a bottle is getting translated into a brainwave, and the computer is watching the brainwaves while the computer is watching the bottle. So the computer's learning the brainwaves and the bottle at the same time, and it's saying this is this, and this is this. And I'm bringing like, these two things are together. This brainwave represents this bottle. This brainwave represents that glass. This brainwave represents this table. And even though we're never going to have the same brain pattern twice,
you still have the pattern.
You still have the pattern.
Yeah. Well, I think what neural networks are able to do in terms of pattern matching and the self-driving, even if you look at that video of like what a Tesla is seeing when it is processing the environment around it, it's fascinating. There is some really advanced.
But here's where it gets weird. Okay, so let's say you capture the pattern of a glass. Now, at first you could say, okay, well, now that I know what the pattern of a glass is, then I could just build that model on the computer, press the button, and the computer sends that pattern directly into the brain. But the weird thing is, if you know that there's no glass there, and the computer's trying to send you a glass, and the glass is interfering with whatever's in your brain right now, how do you resolve that, right? You must have to figure out, like, and where is the glass going to be positioned? Is it going to be on the table? Or is it going to be on the air? Or is it going to look like it's falling off? Will it cause you to have some sort of unintended hallucination? Yeah. Will it cause your reality to crash? Like a program error? It's all sorts of like weird things you have to think about.
The thing I really wonder about is, how do you teach an AI context for the material world, the scale of things, and the way that they interact with each other, that to humans is intuitive, but to machines that don't have the ability to touch and feel and ideate and understand those different things in all these different contexts with really the semantical brilliance that humans have, despite the fact that we're really, really slow at other things that the computers are good at. I really wonder what that is going to look like.
Well, I mean, I would have to say that massive parallelism can make up for chemical latency. In terms of, chemicals are slower, but if you have massive parallel capabilities,
exactly,
you can make up for that difference. I think that people is often repeated that computers are far faster than human beings,
Only at linear things.
And that's a good point. And I think that I think that I actually lost my train of thought just there for a second. So the human brain, for example, has amazing metabolism, right? If you take a glial cell out of a human brain and you put it into a mouse, its memory will improve. At least that's what some studies suggest. And what I'm getting is that there are network efficiencies that our brains have because we're like robots that are billions of years old, right? And they've evolved over billions of years.
We started really with nanosensors on single cells, and we've grown into fully electrically conductive organisms that still have that in them, but are pretty weird.
Yeah. So our network, and not only that, our brains run on like the power of something like a 9-volt battery. Is that right?
I need to check the voltage and or the wattage, but I think it was around a light bulb in terms of the wattage.
Yeah, so it's like, imagine that you have a computer that has trillions of connections and it runs on the same amount of power as a light bulb. Like that's a networking efficiency that does not exist on the internet, and not even close.
Well, that's what's so fascinating about it, is that through the chemical soup and being able to sense the finest gradient of change in that chemical soup, we're able to form such different experiences from moment to moment, because even every single one of our 100 trillion synapses can possess so many states that it's a functional equivalent of, I think people like to abstract the neuron away when they're thinking about neural networks.
Yeah. But let's talk about the ionotropic for a brain for a second, because that ions are particles, right? So now we have a massively parallel particle-based computer. That sounds a lot like a quantum computer, right? Imagine this, but with a massive amount of connections. We're not even close to building something like. So people are like, "Oh man, computers are so much faster." And then here's another. So there's the other thing. There's the savant who's had some sort of brain injury, could have been hit by a car or just born that way, but they can calculate numbers by seeing them, and they see numbers. So they're doing linear calculations.
Yeah, he's got topological calculation abilities.
Right. Yeah. So what I'm saying is that we're running programs that are dominating over other programs. If we inhibited whatever our main program was, we might discover that we can do calculations far faster than a linear computer.
I think our brains just aren't built on needing to do those sort of things because we're so based on interactivity with our environment.
Yeah.
But if you had to interact linearly in some way, you could. Look at even the children who use the abacuses. Yeah. And they can do these insane calculations because they've developed a different tactile sense for how to interact with math.
Yeah. Yeah. And I think it's so helpful to, I think that students should be learning tensor calculus before they learn algebra, before they learn calculus, because when you combine geometry, which is very visual, with algebra at the same time, I think you're giving your own brain, you're giving the human brain an advantage, because now we can understand math in multiple ways, because the brain is very much a multimodal system. The having two eyes and two nostrils and two ears allows for a kind of sensory confirmation,
and two receptors clustered together hundreds of millions of times on a single synapse.
Yes. Yeah.
With the two being not only far more unique, but also forming their own unique signaling cascade.
Yeah.
Versus the two existing in isolation.
Yeah.
And our very most basic signaling unit of this heterodimer or heterotrimer of 2 or 3 receptors clustered together and sensing their neurochemical environment and engaging signaling cascades that are so specific that they can influence that very receptor or gene expression of a range of things that relate to that thing. So it's like the information flow has evolved so well that molecular sensing on the cell surface can directly change the way that different genes are read to influence the environment in the way that best favors survival and evolution and proliferation of that organism.
Yeah.
And that is incredible. Like, if you really think about it, that is completely mind-blowing.
Yeah. So there's no reason in principle why we can't vastly defeat the information complexities of computers just by changing the program that's running up here in our heads.
We just might need a lot of help at the things that they just naturally are better at.
Well, and let's say that we can figure out how to communicate. Let's say we can figure out the communication protocol of the brain, and so you can basically, we can have a web browser terminal that we can access our thoughts with, but then we can also basically say, okay, well, I want to turn off a visual program and I want to run a math program instead. And then we start doing some amazing calculations that are beyond what can be done on computers today, just because we've told the brain we want to run a different program.
Can we please not have ads in our brains? Can we pause to discuss that for a moment?
You actual pause or?
No, I mean...
Oh, you want to talk about it on the podcast? Okay.
I mean, I feel like we should just mention this.
Sure.
Do you want advertisements on your retina? Where do you draw the line?
That's one of those weird. So, what is an advertisement on the biological level? And I mean, there's humans are there's mating. There's all these ads, or basically all these signals between people, and that's a sort of advertising, right? If we got rid of, what would it mean to say, okay, there's no ads or something? I guess it would be to want to inhibit ads is, in a sense, kind of like a evolutionary impulse. It's like imagine a male gorilla wants to inhibit the ads of other male gorillas, right? It's so annoying. Those ads are so annoying, right?
Have you seen the Black Mirror episode? Spoiler alert. Plug your ears if you care about seeing Black Mirror episodes and you haven't, and you don't want any of the plots to be spoiled.
Okay, spoiler.
We'll tell you when.
How are we going to tell them when?
You need to have a friend with you who's seen the Black Mirror episode, and they'll tap you on the shoulder. Is it? I don't remember specifically the number, but there is this one episode where there is a sort of utopia in the usual dystopian way of Black Mirror.
Okay.
And in this environment, there are these credits that you earn from running on a treadmill. You can use to buy food, drinks, toothpaste, and pay to not have ads go off. The ads completely surround you. Mm-hmm. When you are in your sleep pod, your room, the entire walls are this AR interface, and you have the sound directly going to your ears. And if you don't have enough credits, you have to watch the ads. If you look away or plug your ears,
so you earn
it will tell you
by being on the bicycle or something.
Yeah. If you look away or plug your ears, they'll keep making warning noises until you open them.
Yeah.
And finish watching
and potentially fine you for not paying attention to the ads. Yeah.
Exactly.
Yeah, that's very...
So if Republicans maintain control of Congress and we have these sort of technologies, that very well could be our future.
No, wow. I mean, I get it.
I'm being somewhat facetious, but
you want to
maybe a little bit.
You want to avoid a scenario in which you're forced to do something, and you want to maintain a scenario in which you have the choice to define your reality the way you want. And so I mean, I imagine that it's in terms of how the universe is structured. I mean, my hypothesis is that you're going to have a United States of neuroscience, and then you're going to have a North Korea of neuroscience, where I'm just saying in terms of universes created by people, you're going to have a universe that's living in Germany in the year 2018, or you're going to have a neuralized universe that someone creates that's living in the year 1600 in Rome, or I don't know, where there's like Muslims and Christians and and people are afraid to, they're afraid that God can hear their thoughts, or they're afraid that the governor of their state, like if you're in a totalitarian, they could potentially hear your thoughts. And so your thoughts have to be true towards the dictator of your society at all times. And the funny thing is that with NeuroLace, a dictator could actually, in a sense, monitor somebody's thoughts.
Maybe that was the part of 1984 that we missed.
So I would just have to say that it seems like the universe is like, instead of deciding between one possibility or another, it's like creating both at the same time. So you end up, where, it seems like in a long enough timeline, what could happen is inevitable. You know what I mean?
Yeah.
So it's kind of, that's why I'm like, this is, people, we're going to create NeuroLace, and we're going to create artificial brains, and people won't care, because they'll be like, oh yeah, well, it was inevitable, and the universe is a fractal, and it's all mathematics. And there's this there's this conference coming up, but it's on the other side of the planet, and I wish I could go to it, but it's all about how the dendrite is a computer, and it's a Numenta conference. And dendrites they're hugely important it's like that by itself. It's kind of a computer. I don't know, but we're kind of like just wrapping things up anyways. It's kind of like maybe a future podcast we're going to dive deeper into dendrites and dendritic computation. And one thing, I guess, closing out for this podcast, we could talk about, there's a GPU conference coming up in the NVIDIA GPU conference, or GTI conference, and I'm planning to go there because there's many good talks on the topic of artificial intelligence and the latest innovations that people are discovering. And one of those is really interesting because they're discovering that, because if you want AI to like sort of take sensor data and recreate a 3D structure from that, it's actually a really hard problem. But what they found out was that if you give AI some basic 3D models first, then they're finding out that it's able to recreate the 3D model from the sensor data. So it's like I think of it as giving a child a toy to play with in order to catch on to the concepts that are more fundamental to a human's existence. And so they're giving this AI 3D models, and it's more able to handle this. So the idea there, though, is, that could have to do with sensory confirmation. Where if you have two eyes, like let's say a crocodile has two eyes looking two different directions, and my arms are extended out and they're pointed in each direction. And so you have the crocodiles, let's say it's a deep learning program, and, like a neural network, just like we talked about earlier. And one eye is trying to figure out the geometry of the world around it so it can notice some animal passing that it wants to eat, and the other eye is doing the same thing. And and I have to think about how a nerve has like two ends, right? And it's almost like a battery, like a north and a south, right? And so the crocodile is getting each eye has millions of sensors in it, light sensors. And it's going through the neural network, and it's creating like all these brainwaves, which are it's sort of like a brainwave, a 4-dimensional pattern. It's like a electromagnetic tensor field moving with all these different parts moving throughout this system. And at some point, the left eye and the right eye meet, and where they meet, they're confirming each other's model, and the confirmation that each eye is getting is magnifying its ability. So it's an argument for why two eyes have an evolutionary advantage. Is there's sort of a sensory confirmation. The first week of May, I think it's like May 7th, it is about they're going to be talking about that, and it's very interesting. That would make a case for we could potentially build how we potentially might build better AI by making it multimodal, like a human.
And I
brain.
think it needs to be at the very baseline level. The more we can mimic the architecture of how a single synapse functions, the closer we'll probably get to capturing the breadth and the richness of the human experience.
Dun, 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 dun.